All right, today I'm just going to give you a brief overview of what is a trig function. I'm not going to go too in depth in how to use it to solve a problem, but always ask why. I mean, what are these things, right? I wrote some examples here: sine, cosine, tangent, cosecant, secant, cotangent. These get used a lot in trigonometry, pre-calculus, calculus, physics, and all sorts of other fields. But what are they really? Well, in the shortest sense, what these are is just storing every single ratio of every side of every right triangle ever. Okay? So what we know, in short, is that if two angles of a triangle are the same as two angles of another triangle, then they're proportional, right? They're similar, they're proportional. What that means is if we have a triangle here where two angles are the same as another triangle, we use this sine to show that they're similar, and that means that there's some common scale factor where every single side is some multiple of the other. For example, if this one was 3, 4, 5. It could be a decimal or something ugly, but let's just say the nice clean scale factor here is 1 to 3. So this other triangle on the right then would be a blown up version. So 3 times 3, this would become 9. 3 times 4 would be 12. 3 times 5 is 15, right? So these two triangles are similar, meaning it's just like I took one triangle and zoomed in or zoomed out, and that zooming in or zooming out doesn't change the ratio of the sides. The ratio of, say, for example, these two sides here is, let's do it 15, so the hypotenuse first, thinking this is a right triangle, 15 over 9. But if we reduce that by 3, we get that this is 5 to 3. Now that's the same ratio as over here, the same two sides. Right? Because these triangles are similar, that ratio is never going to change. It's just like taking an image of a person and zooming in or zooming out. It's still the same person. The picture is just bigger or smaller. Their nose didn't get larger. Their ear didn't get stretched. It still looks like them. It's just either a big picture of them or a small picture of them. So let's expand that now to right triangles, okay? So what that means now for right triangles is, if we know any angle in a right triangle, right, other than the 90 degrees, well, think about that. Now we've got a 90-degree angle that we know and another angle. We know it is similar to every single other right triangle with those same measurements. Every other right triangle with that angle. So what I mean is, if I come across a right triangle with an 11-degree angle here, and I know it's a right triangle, well, that's similar by, our AA similarity. We know that's similar to every single other 90-degree triangle that has an 11-degree angle in it. Even if it's flipped around or rotated, that's similar to if I have one sitting on its side that's been flipped. Oh, I went off the side there. Let me try that again. If I find one shaped like this, it's still got a right angle. It's still got 11 degrees. That triangle is just reflected and rotated a little bit, but the proportions of all the sides are the same. Okay? So a trig function is simply the stored, saved, known, whatever, however you want to say it, we've known the ratios. I mean, think about that. Since the dawn of time, every single 11-degree right triangle ever formed, ever, has had the same proportions of sides. So if I just ever, one time, throughout the last thousands of years, figured out what the ratios of these sides in this 11-degree triangle are, if I figured out what is the ratio of A to B, or, well, I should, since it's a right triangle, let's do A, B, and C. If I figure out what the ratio of A to B is in that triangle, I could apply it to every time I come across an 11-degree right triangle, right? This ratio over here, I mean, this is just going to be like 3A and 3B, but still the ratio is I mean, 3b to 3a is still b to a. It's the same ratio no matter how large that 11-degree right triangle is. So what mathematicians have done is we've saved every single one of those ratios. So this is the stored, saved, known ratios of the sides of every right triangle ever. Okay, so let's think about that. That means if I come across a triangle with 12 degrees and a right angle, I know it's similar to every single other 12-degree right triangle ever, okay? If only I could somehow figure out those ratios and I had, say, one side. Say I said this side was 3. That gives me the size of the triangle, and I could say, well, you know, if only I knew the ratio of these two sides. I mean, there have been 12-degree right triangles for thousands of years, right, that we've been investigating them. If only I knew the ratios of these two sides of any 12-degree triangle ever, then I could figure out what this missing side over here is. Or if I knew this ratio, again, if I knew it was twice as large, 3 times as large, something like that, then I would be able to find this missing side. And I'll tell you what, these trig functions are in every phone and calculator ever. So your phone / calculator, whichever you're going to be using to do this, I'll swipe over and use my iPad to do it, has all these ratios. Right? All you need to do is clearly communicate to the calculator with the correct name and the correct order which ratio you want. And that's where the naming comes in. If we go back up here to the top, that's all a sine, a cosine, a tangent, a cosecant, a secant, a cotangent are, is you communicating clearly saying, I want this specific ratio. Okay, so let's go back down here. Now, just, you know, as a side note here, how many ratios are there even in this triangle, okay? So let's look at this. In this triangle, okay, this is just a generic A, B, C. How many ratios are there? Okay. And every single ratio is stored in your calculator. Actually, it's calculated by your calculator, but we'll think of it as being stored in there. Okay, well, let's think about this. We could have A to B, or A to C. We could have B to A, or B to C. And we could have C to A, or C to B. I mean, that's every combination, right? We have A to either of the other two sides, B to either of the two, C to either of the two. Now, some of these are a little redundant, right? Like, I mean, if we have A to B, like B to A is just this, like instead of 2 to 3, it's 3 to 2. It's the same ratio, just flipped over. We're not going to talk about those so much at the moment, but every single one of these has a name, right? If we have A to C, like C to A can be useful in certain circumstances, but let's just stick with A to C right now, okay? If we have B to C, then we don't really need C to B. But actually, every single one of these has a name, okay? If we're talking about, say, this pink angle down here, okay? So then, well, that was actually the bad choice because A was on top. But if we're talking about this angle up here, well then A over B, this is our tangent. A over C is our sine. B over C is our cosine. And then these other three are their reciprocals. And so this one is the cotangent, which just means the tangent ratio upside down. Whoops. This one down here is the secant, which just means the upside down cosine. You take the cosine and flip it over. And this one's the cosecant, which just means it's the sine ratio, but flipped over. Okay, I'm going to make one really clear note here. Notice how I originally chose this angle at the bottom and then said, oh, wait a second, that would kind of muck everything up just based on what I'd circled in X. So let me be really clear here, and this will be the last note, is if I draw a right triangle, then I need a way to clearly communicate which angle I'm talking about. Because this ratio of A over C is different from B over C, and I don't know which size I'm talking about unless I somehow signify, you know, okay, I'm talking about the bottom leg or the opposite. Or so what we're going to do down here is we're going to note this. We're going to say, okay, let's say we're talking about this angle theta. Now, theta is just a generic variable. And all it means is we use it with angles. So to any mathematician, if you use theta, I know you're talking about an angle. It's just a Greek letter. Okay, we use it for angles. Okay, now looking at this, if I'm talking about theta here, and I go ahead and label each of these sides, okay, let's call this A, B, and C. In every problem, it's going to change. There's an X, there's a number. But what we do first is we choose our angle. Okay, so I've chosen this angle here. Well, now let's name each side according to this angle. So C, across from our right angle, is always going to be our hypotenuse. Okay, that doesn't change. That's already got a special name. But now we've got two legs. We've got this leg right here next to the angle, and we've got this leg across from the angle. So we pretty clearly name them as across. We call that the opposite leg. So here's our opposite leg across from our angle we chose. And you got to choose that angle first. Okay, and the next two leg, the leg next to, we're going to call the adjacent leg. And now that we've said we're talking about this specific angle, and up here it was all about if we have an 11-degree right triangle, we now know everything's, every single triangle is similar to that. So we're already talking about the 11-degree angle. We've chosen that angle. So now we could say this is our opposite leg. This is our adjacent leg. And of course, across from our right angle is our hypotenuse, right? If we're talking about, let's see. Oh, I had one on its side. What if the 11-degree angle's over here now? Well, now still, this is the hypotenuse. This is the opposite leg, and this is the adjacent leg. So once we choose that angle, now we can talk about which side of the triangle is which, oriented around that angle. Okay, so down here, once we've chosen that angle, we can call each ratio by name. Okay, the sine of the angle, so we choose that angle first. Here's our input, and that input into our function is an angle, is equal to the ratio of the opposite leg over the hypotenuse. Okay, so very clearly, if I come across any 11-degree right triangle, then the ratio of the side across from it to the hypotenuse, so that ratio of opposite leg over hypotenuse is the same in every 11-degree right triangle, and my calculator can tell me that. I could actually go over to my calculator here, and I could say, all right, well, what is the sine of 11 degrees? So the ratio of those sides is always going to be 0.10, or roughly, I should write it on here. So 0.190, or the sine, this is just an example, the sine of 11 degrees is going to be this irrational decimal place going on forever, which is around 0.190, because that keeps going, which is around 190 to 100, or to 1,000, right? So that is an approximate ratio, right? Now, I'm also going to declare the rest of mine. So I've got what is the sine ratio. Very clearly, once I chose the angle theta here, then I know, okay, my sine is the opposite leg over the hypotenuse. That's the ratio the sine is talking about. Okay, so let's do our other two that we're going to talk about today. So the cosine of theta is equal to the adjacent leg over the hypotenuse, and then our tangent of theta is equal to the opposite leg over the adjacent leg. All right, so those are the three main ones that we are talking about today. Again, the other three that you'll come across are just those flipped over. So the tangent is the ratio of these two, the opposite and adjacent. The sine is the opposite over hypotenuse, so it's just the ratio of these two sides. And the cosine is the adjacent hypotenuse, so it's just the known ratio of those sides. So again, going back to the beginning here, a trig function is just the stored, saved, known ratios of the sides of every right triangle ever. If you come across a right triangle with a 17.18 degree angle, your calculator knows the ratios of all those sides and it has names for it. You could plug in what is the sine of that angle, and it'll tell you the ratio of these two sides in that triangle. If you want different ratio, okay, ask for the tangent, ask for the cosine, but the ratios of those sides are already set in stone. I'm going to make another video where I introduce these separately and we do a lot of practice problems, but that was just a brief overview of what is a trig function, why do we use it.